cut from now maybe. Okay. And the next chapter is chapter 5. And chapter 5 is for the, you know, remember that the equation we derived in the chapter 4, they are all in the integral form. Okay. And for the integral form, because that is in the integration, right? All the terms, those kind of terms is in the integration. Either, you know, we integrate the things inside inside the control volume, or, you know, do a surface integration, right? For example, we're using this mass conservation as an example, right? So you see that the first term is the integration of density on the control volume. The second term is an integration of this, mass flux term on the control surface. So they are all integral form. And for the integration form, okay, you know, they have the advantage and the disadvantage. The advantage of this integration form is that they are usually, okay, mathematically not difficult. Okay, think about that all those example problems we go through in the last chapter. Okay, it didn't involve very difficult math, right? It won't usually just very simple algebra equation, right? It won't ask you to do very complicated, integration, differentiation, those kind of things to solve this equation. Okay, this is the advantage of this one integral form, and but it also has a disadvantage. Okay, what's the disadvantage of this one? You know, is that for the integral form, okay, because that we try to solve the things in a large control volume, right? Then we integrate the things inside the control volume or across the control surface, okay. And we know that integration is like mathematically, right? Integration is something like a summation, right? It's like we like to get that what the overall result will be, right? Like that's the meaning of the summation, and that's the meaning of the integration. So in other words, when you try to solve this integral form of the equation, okay, basically you try to looking through this control volume you defined as a whole. Okay, so it's like you try to thinking about that your flow inside your system, your control volume, you know, is a bulk, you know, it's one item. A whole stuff there. Okay, which means that the result you get, okay, you won't know anything happened inside this control volume. You do not know anything inside specific value. Okay, so if, for example, if I define, remember that we have an example problem, right? Like if we have a nozzle, right, and we have the water coming out, right, to heat this plate vertically, right, and then asking us that what this force is required, right? We have one example problem like that, okay. And when we define the control volume, we define this way. We can define the control volume in this way as CV, okay. And from the equation, okay, if we solve that integral form of equation, we can only know what happening between the interface of this control volume and this solid surface, right? We only know what happens as this interaction, as this boundary of this control volume, like the force, right? How much force is required, okay? And we want to know that inside this flow motion, okay? For example, what's the local velocity at this point? What's the local pressure at this point? What's the local velocity at this point? Local pressure at this point? What's the local density here? You want to know that. Okay, in another word is that, since we, this integral approach, right, we try to think about this whole control volume, we analyze it as a whole, we were not able to know what the specific point, those flow properties at the specific point inside. But the only thing we can get, okay, is that, what's the gross flow effects, such as the force or torque at the boundary of this control volume, or what's the total energy changes. So this is the limitation of the integral approach. Okay, But if we really want to interested is that what's the local value of this flow, right? We want to know what's the flow value velocity at each point inside. How we are going to solve that? So that will be resolved related to the second way to develop the governing equation, which is called the differential approach. Okay, so differential approach, basically from this term, you will know that the governing equation you derived will not be in the integral form, will become differential equation, either the ordinary differential equation or partial differential equation. There's no that integral sign anymore. Okay, you only have that this d something or partial something. Okay, those kind of terms. Okay, ordinary derivative or partial derivative. Okay, and if we can develop the equation, those equations, okay, in the differential approach, okay, so which means that we can study the fluid motion, okay, for at every local point, or in another word, we can try to study that the behavior of very small fluid particle. We can find any the motion of very small fluid particle. Okay, so this is the difference between these two methods. So in the last chapter, we're focusing on this integral approach, right? We derive those fundamental laws, for those for control volume in the integral form. Okay, and then in this chapter, we will focusing on the differential approach. Okay, what the differential approach means? The differential approach means that the equation will be in the differential form, either be the ordinary differential equation or partial differential equation. Okay, and by this method, if we can solve those differential equations, we will know that the those flow quantities, the density, the pressure, the velocity, okay, the temperature, actually each local point inside this fluid. Okay, and that's why we want this differential approach here. But you will know that, okay, this differential approach mathematically will be more complicated than the integral approach. Okay, because we know that the fluid motion, because we want to get the flow, the fluid property at each point, right? And also this fluid motion is very complicated, right? In a lot of cases. So in many cases, okay, after you get these differential equations, you won't able to solve it analytically. Okay, only for the very small, very simple, okay, very fundamental benchmark problems, you may be able to derive some, analytical solution. And a lot of time you have to using the computer to solve it. And that is the field of those computational fluid dynamics, CFDs things, okay. And here is another example. This picture showing you that the difference between the analytical, this integral approach and the differential approach. Okay, so this is the airflow, okay, across an airplane. Okay, we have the airflow flow over airplane. Okay, this is red is airplane, and in the integral approach, okay, in the integral approach, we just try to think about define control volume and think about all the fluid inside this control volume as a whole, and as a whole atom. And since it's the integral method, right, we won't able to know what exactly happened inside this fluid, but we do know that using those fundamental law, either the momentum equation or energy equation, right, we can find that at the boundary, right. For example, for this one, at this solid fluid boundary, if I want to find the drag force, we want to find the lift, the overall lift force for this air, this moving air to this airfoil. We can just using the integral form of momentum equation to solve it, because that those value we want to find, right? This drag force, this lift force, this is the property at this solid fluid interface. Yeah, in other words, this is at the interface at the control surface of your control volume. It's not inside the fluid, those value. So you can using the integral approach to solve it, no problem. Okay, but in another word, okay, if what we want to say is that we want to get the detailed flow structure for the flow over this airfoil. Okay, for example, like if it's a supersonic flow, we know there will be a shock wave generated on the top. Okay, I want to know that what's the flow velocity changing, on the top and on the bottom. We know that pressure on the bottom is larger, pressure on the top is higher. Sorry, pressure on the top is lower. Okay, so that's why you have the lift, right? And we know that there will be a flow separation at some point here when the velocity is large enough, and those complicated things, and especially like if we have the turbulence, right, and we have those wake generated, behind the tail of this, this airfoil. Okay, and this wake usually, will causing more, you know, um, will cause some pressure, loss. Okay, and then giving you, more drag. Okay, for this airfoil. And this kind of complicated things. Okay, you won't able to solve it using the integral approach. Okay, you have to go back to the differential approach so that we can try to that, for example, if in the CFD, okay, we need to generate this numerical grid points and maybe verify. Okay, and then for each numerical point here, grid points here, we try to guide what the for each local point, what the local temperature, what the local density, what the local pressure, what the local velocity will be, and then we can using some visualization method like either the contour or the vector plot. We can see that what the flow structure around for the air around this air off and air foil. Okay, so this is the biggest difference of the integral approach and the differential approach. Okay, and so now the question is that how we derive this differential approach equations, right? How we derive this governing equation, fluid dynamics governing equation, those conservation of mass, momentum equation, energy equation. Okay, how we derive those equations in the differential form. And it's the same idea as the way we derive for the integral form. Remember how we derive this those fundamental equations in this integral form? We just define a control volume, right? And then we see that how many moving in, how many moving out, how many stay in, and that will be equal to the overall change, right? That is the way we define it in the integral approach. And we have control volume, and this control volume has a volume of V here. We will basically, when we try to derive the differential form of the governing equation, we will also do the same thing. The only difference is that instead of we define, we try to using a finite size of control volume V. We will using a differential control volume D of V. Okay, we try to derive those governing equations still on a control volume, but that control volume will be is a differential control volume, which means that this value will go to 0, go to limit, go to 0. Like if you have this delta x, delta y, and delta z, and after you derive those governing equations, you let this delta x, delta y, delta z go to 0, go to limit, go to 0. Then everything, this control volume will collapse to a single point in the center. Then you get the governing equation at this point, rather than you get a governing equation for the whole control volume. Okay, so this is the way we did it. Okay, just we still derive using the fundamental law. Okay, based on the control volume, but in the end, we will make this control volume, their volume go to limit. Okay, go approach to 0. So that this control volume will collapse to a specific point at the middle. Then we get the governing equation, which is working locally for this point. So that will be the differential form. Okay, which will be for this specific form point. Okay, and so to do this, let's use first using the mass conservation as an example. Okay, and this is just recall what we have the integral form of the mass conservation, right? So this is the mass conservation we have in the last chapter. Two terms. The first term is the net rate of the change of the mass inside the control volume, right? And the second term is mass flux, okay, term like fluxing out, flow out, through the control surface. Okay, let's still, using this correlation, but now we try to derive, mass conservation for a differential volume. Okay, And what the differential volume is defined. And the define of this differential volume is based on the differential control volume is based on the which coordinate system you use. Okay. We will do two kind of coordinate system. The first one is rectangular coordinate system. Okay. And assume that we have this XYZ coordinates, and we have a very tiny control volume. And okay, and this control volume is inside is for fluid. Okay. And assume that the center of this control volume is O. We'll have this at point O, and also that this control volume will be in this XYZ coordinate will be a cube, and x direction length is dx, y direction is dy, and z direction is dz. So the overall volume will d of v will be just equal to dx times dy times dz, right? So this is the overall volume dx, dy, dz. And so if we want to apply the mass conservation, we need to go back to using this equation, right? So we need to calculate this term and this term, these two terms for this small control volume. So let's calculate the second term first. So this is term of the, mass flow, okay, the net rate of the mass flux flowing out through the control surface, right? So for this control volume, we have 6 surfaces, okay? We have the left surface with the negative x surface. Right surface is the positive x surface, right? Because it's in the positive x side. And the back, the bottom will be negative y surface. The top will be the positive y surface, right? The back will be the negative z surface, and the forward will be the front will be the positive z surface, right? So we have 6 surfaces. So which means that for this control volume, we will have 6, inlet or outlet. Depend whether or not this each phase is inlet or outlet is determined by the flow direction, by the velocity direction, right? So we have these 6 phases. So we need to consider that what the mass flux flow in or flow out from this 6 surface. Okay, 1, 2, 3, 4, 6, 5, 6. So let's first take a look at the right surface. This surface here. Okay, for this surface, we will have the surface area dy times dz. Okay, so this area will be dy times dz. And so if we want to know that how much of the, mass will be flowing out from this surface, will be that u times dv, right? The rho of u, because at the x direction, right? This v become u, and times this area. Okay. So we need to know that we also need to know the rho. So we need to know the rho and the velocity at this surface. Okay. And how we do know that? We assume that we know that this rho and u at the center point O. Okay, because at the end, right, everything will be collapsed to this center point. Let's assume that we know that this rho and the velocity u at this center point O. Okay. And how we know that the velocity at this surface? Then we can using the Taylor series, because that from O to this surface is the only displacement is a positive delta x over 2, right? Delta x over 2, because that's overall is delta x, right? The overall is dx. So from the distance between O and this surface is dx over 2. Okay, and then the right surface, the density at the right surface will be x rho at x plus dx over 2. Assume that this O has x, y, z coordinate. Okay, this O has so this O will be x, y, z. Okay, so coordinate for this center point O is x, y, z. So on this right surface, the x will become x plus dx over 2. Okay, and then we can just using the Taylor series. This is a small difference, right? So this value can be calculated based on the derivatives. Rho will be plus partial rho partial x. The reason we're using partial is that because rho is not only a 1D, this is not only 1D problem, it's 3D problem, right? Rho is also dependent on y and z. So now this is only give you the density gradient on the x direction. Okay, and this gradient times this delta x over 2, and also plus some higher order terms will give you this value. And if we neglect these higher order terms, okay, because this term is in the order of this dx squared, dx cube, and dx third, and we know that this dx is very small value, right? So that this square of dx will be much smaller than the dx itself. So this term can be neglected. Okay, all the higher order term can be neglected. So the only thing left is will be this one. This give us that what the density at the right surface, right? Rho of x plus dx over 2 equal to rho plus dx partial x partial rho partial x dx over 2. Okay, and so this is for the rho. And similarly, okay, because we want to calculate the mass flux on this surface, we also need to know velocity. Assume that the velocity at the point O is u. So we can calculate that the velocity at this right surface will be u of x plus dx over 2. And using this Taylor series again, we'll get the result that it will be equal to u. This u is the velocity, and this u and rho is the velocity at this point O, okay? Plus partial u partial x times dx over 2. Right? After you have these two terms, and if we want to calculate what's the mass flux flowing out from this surface, and because that this is positive x direction, right? And this u we define as this positive x direction, so u will be going in this direction, positive x direction, and this surface area is also on the same positive x direction, so that you will have positive sign for it. Okay, when you do that v dot da, okay, when you do these things, okay, because this is the mass flux, right? So when you have v dot da, you will have a positive thing. So just rho times u times the area. What the area is dy times dz, right? For this surface area. Okay. So the mass flux at the right face will be just this rho value times this u velocity and times this surface area, right? And if you rearrange it, you can rearrange it in this form. Okay. And so this we're handling one phase. Remember, we have 6 surfaces, right? So we need to also handle the other 5 surfaces. So let's consider the negative x phase, okay? So this on the left, this surface here, this negative x, this one here, this one here, okay? And you can similarly using the Taylor series, okay? You can guess that what's the density and the velocity u, okay? Because it's also x direction, so what's the velocity u on that negative x surface, okay? And the difference compared previously is that you need to, because that this dx is going into negative direction, so you need to change the positive sign to the negative sign here, okay? And so this will be the density and the velocity at the left surface, left face, okay? And for this one, okay, because that is this u, because on the left surface, right? So this is the x, right? And this is right surface, and because it is x surface, and remember when we define this u, if this u larger than 0, is always going to the positive x direction, okay? And because the surface area is always in the opposite direction of this positive u direction, right? So that means that when you do that this rho v dot da, you will have a negative sign for this surface. Okay, so that's why is that when you try to calculate the mass flux on this surface, left surface, you will have this negative sign here, and this negative sign is due to this directions different between the velocity and the surface normal. Okay, and this negative sign times rho times u times da, da again is dy times dz, and you will get this value. Okay, and you compare these two, you see that this term and this term is same, but this term and this term they are has a opposite sign. Okay, so now we're handling two surfaces, right? And let's consider all the other 4 surfaces, right? So the bottom, the bottom will be negative y, the top will be positive y, and the back will be negative z, and the front is the positive z, right? For the negative y, it now will be, when you calculate it, will be partial rho partial y times dy over 2, right? Because it's in the y direction, and it's a negative y, so that's why you have this minus sign here. And also it's due to that velocity as some normal surface area difference, you have a negative sign here. On the top y, again, you have the plus and plus here. You get this result. And also similarly for the negative z and positive z. Okay, now you have this is the surface mass flux for all the 6 surfaces of this differential control volume in this rectangular coordinates. Okay, And then when we try to calculate this integration, right? This integration was this is a integration on the whole control surface, right? For this mass flux. So in other way, this means that you need to add all these 6 together, right? You if you want to evaluate this one, if you want to evaluate this value, you just need to add all this surface flux, okay, for all these 6 surfaces. Just add it together. If you add these 2, you see that this value and this value will be cancelled because they will have negative sign, positive sign, right? So this is gone. And when you add these 2 will be cancelled. When I add these 2 surfaces, this value and this value will be cancelled because you have negative sign, positive sign. And similarly for the z, okay, negative sign, positive sign. So the only thing left is this one, and this one, and this one is identical. So when you add them together, this one half become 1. This one is identical. When you add them together, one half become 1, and same for this one. Okay, so when you add all these mass flux for these 6 surfaces together, okay, your final form for the mass flux for this surface, okay, of this differential control volume will be just equal to this equation. Okay, it's telling us that you know, for the integration for the whole surface, rho v dA will be just equal to this one plus this one plus this one, and times dx dy dz. This dx dy dz is the volume dv, right? And you can even further to make it this equation simpler, because that if you look in this one, so this will be just equal to partial of rho u partial x, right? Because that is u d rho dx, this is rho du dx, right? So this is just the differential by parts of this one. Similar things, this you can put this v inside. This partial rho v partial y will become this 2 term. So this one will become this 2 term, differential by parts, and this term will become, and if you do differential part, it will become this one. So you can even write a shorter form, just will become partial rho u partial x plus partial rho v partial y plus partial rho w partial z. So this will be the overall surface control mass flux, across this control surface, and leaving out from the control volume. Okay, so now let's go back to this equation. We're handling this one, and now if we know this one, we can get the equation. Okay, so next question is that how we find this the change of this mass inside this control volume. That is much simpler. Okay, the change of the mass inside the control volume. So this is what we get for the surface flux. Okay, and the change of the overall mass inside this small control volume, okay, is given by partial rho partial t rho dv, right? And remember that we consider that this is a differential control volume, which means that this dv will go to be a very small value, right? Eventually, right? So which means that this rho, okay, you can just take it out. Okay, because that when the v go to 0, this rho will be approached to that density at that origin point O. Okay, so that means that this you can see that this go to the limit. Okay, you can just take this rho out of this integration, so this will become partial t rho times v. Okay, partial t rho times v. Okay, dv will be this v is given by dx times dy dz. This will give you the dv, right? This is the volume of that. So this is the volume of that differential control volume. Okay, and since that when we define this control volume, we define is stationary control volume. Okay, so which means that this dx dy dz is not changing with time. So you can take this dx dy dz out. Okay, so this term will become this d rho partial t dx dy dz. Okay, and remember that so now we get this term. And remember that for this mass conservation, we only have 1 term, right? This one plus this one equal to 0. Okay, so now we get the result for these 2 terms, which means that this one plus this one will go into 0. Right? This one plus this one going to 0. And you'll see that these 2 terms both share this dx dy dz, right? So you can divide the dx dy dz. You can cancel it out on the both sides because the other side is 0, right? 0 divided by this one is still 0. And then your final result will be this partial rho partial t plus the things inside equal to 0. Okay, partial rho partial t plus partial rho u partial x plus partial rho v partial y plus partial rho w partial z equal to 0. And this is a governing equation, okay? The mass conservation equation in a differential form. You see that this is the mass conservation, right? Because this is directly derived from this integral form. So it's still mass conservation. But now you see that all the integral operator is gone. The only thing left is this partial derivatives. So that's why this is a differential form of mass conservation. Okay, and so this equation will working for this local point of O, because when this dx dy dz equal to 0, everything will be collapsed to this O, right? So which means that for the differential form of equation, they will be valid for any point inside this inside of fluid, right? Because that this will be working everywhere inside each individual fluid point local location, right? And this equation is also called the continuity equation. Continuity simply means that mass is conserved, right? There are no loss of the mass, Okay. So now you see that how we derive a differential form for this mass conservation. Okay, and because this is differential, not integral, right? So this will be working for the local points inside the fluid. Okay. Do you guys have any question for it? How we derive this? You can see that we still derive this from this control volume. Okay, but now this control volume is a very small one, very small one. Okay, and you know, and eventually, you know, if we do this, you know, mass conservation on this small differential control volume, we can derive this differential form of the mass conservation equation. No question? Okay, so if no question, so there's let's continue. Remember that we have this form here: partial rho u, partial x, partial rho v, partial y, partial rho w, partial z. Mathematically, okay, there is a operator can make this equation become more shorter. Okay, this is we have a divergence operator. Okay, this is lambda. This operator lambda is defined as this I partial x, g partial y, and k partial z. So that we can write this partial rho u partial x, partial rho v partial y, partial rho w partial z. So this lambda is a vector, okay, as a vector product between this you know, this operator divergent vector divergent operator times this rho v, okay, because this is I of partial x, right, plus g of partial y plus k of partial z, right? So if you do a vector product with another this v, right, rho v, right, so it will be rho of u I plus rho of v g plus rho of w k, right? And you do this vector product, so this I times this one, so the only thing left is rho u, right? Because this I and g, I and k, they are perpendicular. When you do this dot product, it will be 0, right? So this will give you that rho of u, right? And then same thing for this g, you do the do the vector product between these three terms, and when g dot I and g dot k become 0, so only thing left is g dot g plus rho v, and the same thing for the k, right? You get rho w, okay? You get these things, and partial rho, okay? So forget partial rho v because you have partial here, okay? Partial and partial z, okay? So this is a vector form, how you can represent this term. And what this term is called? You will see that this term, okay, this term is from this this term we derive when we derive it is coming from this mass flux across the this control surface, right? And this, and also this, you can see that this term is only related to the velocity. If velocity is equal to 0, okay, if u equal to 0, v equal to 0, w equal to 0, all this term is gone, okay, it's become 0. So this term here is we will call the convective term. Convective means that you have the flow motion, okay. So which means that all these three terms is due to the flow motion, right? Because it's related to velocity, okay. And this convective term can be read as this is the this is the lambda dot, okay. This we call the divergence of this density times velocity vector, Okay, so if you substitute this correlation back to this equation, we can write everything in this form. Okay, divergence of rho dot v plus this partial rho partial t equal to 0, and this is called the vector form of the mass conservation. Okay, this is vector form, and this is the component form, right? Because that this you can think that this is just that this vector form written in the component way, right? We write that vector in x, y, z. Okay, and so why we want to use this vector form? Two things, right? The first thing like is more clean, more short, right? The second thing is that later on I will prove you that this vector form is independent on which coordinate you use. Okay, which means that this vector form you will always valid no matter your coordinate system is rectangular coordinate, polar coordinate, cylindrical coordinate, spherical coordinate. Okay, it doesn't matter. Okay, this is the vector form is usually independent on coordinate system. It's just like if it's a rectangular coordinate, this operator is defined by this way. But if you use cylindrical coordinate, you will have different representation for this operator for the cylindrical coordinate. Okay, we will talk about that later. And two special cases. Okay, the first one is that if density is constant, this rho partial rho partial t is 0, and this rho density is constant means that this, remember this operator, right? This nominal operator, this divergence operator, is only on the derivative on x, y, z. Is only on derivative on the spatial. Okay, so if your rho is constant, which means that your rho is not changing on spatial, so you can take this rho out. Okay, so everything left will be just delta dot v equal to 0, right? Because this is 0, and you can take this rho out, and then you divide rho on the both sides. The only thing that left is delta v dot delta dot v equal to 0, not delta nominal dot v equal to 0. Okay, and if you write it in the component form, will be partial u partial x plus partial v partial y plus partial w partial z equal to 0. And that's why this one is called the divergence operator, right? So this means that in compressed flow, the divergence of your velocity field is 0. Okay, and the second special case is the steady state flow. Steady state flow means that this partial t term is gone, right? So this is equal to 0. So the only thing left is this one. Okay, the only thing left is the delta. So this is nominal dot rho v equal to 0. Okay, and so that you have partial rho u partial x plus partial rho v partial y plus partial rho w partial z equal to 0. Okay, so this is the second special case. All right. And do you guys have any questions so far regarding that how we get this differential form of mass conservation? No. Okay, so let's do an example problem to how to use this equation here. Okay, how to using this equation here, this one or this one in the component form. Okay, so please read this one first. Okay, so this is a two-dimensional problem flow in an xy plane. Okay, so we know that the coordinate is a rectangular coordinate, so we can use the equation we developed before. And it's xy plane, and so which means that nothing changes on the z direction, right? So you know that anything related to partial z, we can assume equal to 0. And the u velocity is given, and So the question is asking us that what the V velocity will be. And also we know that the flow is incompressible, right? It's showing that incompressible. So that let's using the steady state, not steady state, that's incompressible flow mass conservation. For the incompressible flow, this will be the mass conservation, partial U, partial X, partial V, partial Y, partial W, partial Z. You add them together equal to 0. So this will be the mass conservation differential form, right? And also because it's 2D only on X, Y, so this term is go to 0. Okay, nothing change on the Z direction. Okay, so the equation become partial U, partial X, plus partial V, partial Y equal to 0. And U is given, U equal to AX. And the question is asking us is to ask how to find V. Okay, so it's just to try to solve this differential equation, right? So you substitute this U equal to AX into here. Okay, so if U equal to AX, partial U, partial X is just equal to A, right? So this term will become A, okay, which giving us that partial V, partial Y will be equal to minus A. And if we want to find the V, we just need to integrate on this side, on the left side on Y, and on the right side also on Y. Try to find that what this V value will be, right? So because that, so this is when we try to, if we want to find the V, we just need to integrate on this partial V, partial Y on the dy. Okay, but because that this is partial derivative, not the not the direct derivative. Okay, which means that the integration of this one, okay, will give you a constant, and that constant will contain anything not y, which means that that constant can be anything a function of x and t. Okay, because this one you will integrate this one, right? Because this is only partial, you only integrate this v on the y direction. Okay, so which means that when you integrate this one, you will bring a constant as a result, and that constant, unknown constant, can be anything not y, which means that can be an arbitrary function of x and t. Okay, so when you do this integration, you will get this result. Okay, v will, because this is minus a, right? Partial v, partial y minus a is constant. When you do the integration, you will get minus ay and plus the unknown function of x and t. Any arbitrary f(x,t) can be, and this can, we do not know this value. This value, if you want to know it, you have to know the boundary conditions for this differential equation, because usually if you want to get the exact solution for the differential equation, you need to know the boundary condition. Okay, you need to know at the boundary at this range what the result will be. So we won't know this. Okay, so for this problem, the solution will be just this one. Okay, and remember that this any function of f(x,t) is global. Okay, because why? Because that if you put this result, you can try it yourself. You just put this result back to this governing equation. No matter what this f value will be, this governing equation is still valid. Why? Because that when you do this partial y for this term is always 0. Okay, and this showing you that how to use this mass conservation, okay, to get the detailed velocity field inside this fluid, right? And for example, if we know the boundary condition, we can find this f value will be. Now we know the exact flow velocity field, inside this whole fluid domain, fluid problem, right? So this is the things that you won't able to get from the integral form of equation, right? It won't give you this specific u and v velocity inside. Okay, and let's take another example problem. Okay, so this is a piston, piston cylinder problem, right? And So at this moment, this piston is moving to the right with this v equal to 12 meters per second. Okay, and the density inside this at this moment, the density inside is given and as a constant, which means that this density inside this cylinder is not a function of x. Okay, not a function of the spatial. And we also assume a linear velocity change, right? Because we assume that the velocity at this wall here is 0, and the velocity at this piston will be the same velocity as this v. Okay, so the velocity of the air inside will be a linear function regarding to x. This is the assumption. Okay, so u as a function of x will be equal to v times big X divided by L. Okay, so the question is asking that no, the rate of change of the gas density at this instant, and also that what the average density will be, right? So we want to know this partial rho partial t. So the rate of the change of the gas density means the partial rho partial t, right? And then we also want to know the average density rho as a function of time. So when you regard the partial rho partial t, we know that this is a transient problem, right? This is the mass conservation differential form. This partial rho partial t is what we found. We want to find, and then we just need to find this this term. We can get the result, and this term is the mass mass flux across the control volume, right? So if you define the control volume for this specific moment, okay, is as this just as this cylinder here, and we know that it's moving to the right, so we know that there will be mass flux leaving from through this right surface, right side face. Okay, so we just write this because also this is one-dimensional problem. Okay, it's only on x change, so there is no change on the y and z. So this term is down, this term is gone. So we only have this partial rho u dx partial x plus partial rho t equal to 0, and this partial rho t is what we want. So we only need to find this partial rho u partial x. Okay, and partial rho u partial x, you can do the derivative by part, so it will become minus rho partial u partial x, and minus u partial rho d partial rho partial x. And because that we assume at this location, okay, moment rho is not is a constant spatially. This rho value will be changed with time, but this rho is only a function of time, not a function of x. Okay, because it's assumed the gas density uniform on the spatial. So which means that when you have this partial rho partial x, this term is gone. Okay, so at the end, okay, you will have this because rho is only a function of time, right? So now you can change this partial derivative to the derivative because rho is only dependent on t. Okay, d rho of dt will become minus rho du dx. Right? Partial u partial x is known. It's from this correlation u equal to v x over l. Right? It's given. And then the question is asking rho. So this is the differential equation. Okay. And we just need to partial u partial x equal to v over l. Right? So we substitute the partial u because vl. You can just try to solve this ordinary differential equation. This is an ordinary differential equation for the rho as a function of time. You just move everything related to the rho to the one side, and everything related to the t to the other side. Okay, and then you do integration on the both sides. This integration on the rho from rho 0 initial stage to some instantaneous stage, and this is from the initial t from 0 to some instantaneous time t. We do this integration to solve this equation. The left-hand side will give you a long rho. The right-hand side will just give you v over l times t. Okay, and also this L here, we need to be careful. This L is also not a constant, right? This L is this length, and we know that this length is changing with time. So this L is changing with L0. L0 is the initial stage of length plus v of t, and this v is the changing speed of this piston. You substitute here, you do integration, and you get the result. And you get this result from knowing that at t equal to 0, you have the initial condition for the rho equal to rho 0, and for the initial length equal to L equal to 0, right? So this gives you a result that showing you that what's the density as a function of time, right? So this will give you the second result, right? obtain an expression for the average density as a function of time. And you see that we solve it directly by solving this mass conservation equation. Solve this differential equation. Okay, and at this moment t, if you make a t equal to 0, you will get that what's d rho dt at t equal to 0. You'll know that at t equal to 0 was the first question asking the rate of change of gas density at this instant. Okay, so you have this rho t, so partial t will be this value. We know that t equal to 0 will become this value. All right. Do you have any question for this example problem? No. Okay, so today we go through that how to derive this differential form of the mass conservation, right? And then if we can solve this differential equation with some boundary condition or initial condition, we can solve the whole flow of properties. Okay, and so this is one conservation equation. The next class we will continue to do that how to derive this mass conservation in other coordinate systems, like the cylindrical coordinate system. Okay, and remember that this equation we use here is only for the rectangular coordinate system. And if you do not have any question, I will just finish here. And before you leave, please go to your Blackboard, and there is a quiz, so that you can do for today's, let me see if the quiz is available. Yeah, if the quiz is available, just finish it. So for today's attendance. Okay, I'll see you guys on Friday. Okay. Bye, everyone.
Have a good day, Professor.
Bye. Yeah.
Professor?
Yes, you have a question?
Does it matter if you get the question right?
Sorry, I cannot hear you clearly. What's your question again?
Does it matter if we get the question right?
No, it doesn't matter.
Okay, thank you.
Yeah, it doesn't matter. Yeah. Okay, bye.